In the world of math, some things are just not what they seem. There are equations that hide secrets, formulas that can literally change their shape right before your eyes. So today, we're going to be detectives. We're going to uncover the secrets of one of the most interesting shapeshifters out there.
Okay, let's just dive right in. Take a look at this equation. I know, it looks like a total mess, right? Just a jumble of variables and coefficients. But what if I told you that this single line of code, this one formula, could be a perfect circle, or a pair of lines crossing each other, or even just a single dot? So the question is, how on earth do we know what it's hiding?
Well, this thing is what's called the general second-degree equation, and you can pretty much think of it as a master recipe for a whole family of shapes. It's the blueprint for every single conic section you've ever heard of, and believe me, even a few you probably didn't expect. The real key, the magic to this whole shape-shifting business, lies in these letters: A, B, C, F, G, and H. Now, they're called coefficients, but let's just call them the ingredients. It's kind of like baking, If you change the amount of flour or sugar, you get a completely different cake. Well, here, you change the values of these ingredients, and the final shape totally transforms.
So how do we crack this code? How do we figure out what shape is hiding inside this equation? Well, the good news is we don't have to guess. There's a system, a process, and it all starts by calculating our very first clue.
And that first clue is a special value called the main determinant. We show it with the Greek letter delta. All it is a number we get by mixing our ingredients, the coefficients, in a very specific way. And this one number, it's our first and most important decider.
Now what's really cool is how we find this delta. You can see it here. We just plug your coefficients into this little 3x3 grid, which is called a matrix, and the number that pops out from that calculation basically sends us down one of two paths. If delta is not 0, we're dealing with one of the famous true conic sections. But if delta is 0, well, that's when things get a little weird.
So let's go down that weird path first. When delta equals 0, we enter the world of what are called degenerate cases. This is the part where all those grand, elegant curves kind of collapse into something way, way simpler. So check this out. You see this equation, you see the x squared and y squared, and your brain just screams circle, right? But if you do the math and calculate its delta, you get 0. And when you graph it, it's just a single point. The whole complicated equation just collapses into one tiny spot.
And it's not just points. This next equation also has a delta of 0. But this time, it doesn't shrink down to a point. No, it actually represents two perfectly parallel straight lines. It's like a geometric echo.
And there's one more possibility in this strange little world. For this final example, delta is also 0, and it gives us a pair of straight lines that actually cross at a single point. So the big takeaway here is really simple. When delta is 0, just forget about the fancy curves. You're dealing with the basics, points and lines.
Okay, so let's get back to the main path. What happens when delta is not 0? Well, this is where we find the true celebrities of geometry, the conic sections. I mean, these are the shapes that describe everything from the orbit of a planet to the design of a satellite dish. They're a huge deal.
And what's so beautiful is where they all come from. The parabola, the ellipse, the hyperbola, they aren't just random shapes. They're all family. Every single one of them is just the shape you get when you take a slice out of a cone at a different angle. It's just such a simple, elegant origin for so much complexity.
So, we know we've got a true conic, but which one is it? A parabola, an ellipse? To find that out, we need our second and final key. And don't worry, this one's a much simpler calculation. We represent it with a lowercase delta.
And here it is, the solution to our mystery. All we have to do is look at the sign of that lowercase delta. If it's 0, you've got a parabola. Boom. If it's positive, you've got an ellipse. Or its super special case, a perfect circle. And if it's negative, you're looking at a hyperbola. It's really as simple as that.
So now we have all the clues. We've got our two keys, the big delta and the little delta. It's time to put it all together into one single unified guide.
And there you have it, your complete cheat sheet for decoding any of these big, scary-looking equations. It really is just a simple two-step process. First, you check the big delta. Is it 0 or not? That tells you if you have a degenerate case or a true conic. Then, you just check the sign of the little delta. That pins down the exact shape every single time.
Galileo once said that mathematics is the language in which God has written the universe.
And when you really look at how a single, simple equation can so elegantly describe so many of these fundamental shapes, from the path of a baseball to the orbit of a planet, you really start to get what he meant.
So, the next time you see some complicated equation, just remember the secret it might be hiding inside. I mean, if this one formula can contain so much variety and beauty, it just makes you wonder, right? What other amazing truths are out there hiding in plain sight, just waiting for us to find the key?